Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. We have been discussing about turbulent flows. We looked at the Rance equations for the incompressible flow and compressible flow, and we also started discussing about how to basically address the closure problem in the turbulent flows. So, the Reynolds stress that we get, how do we basically model them? So, we looked at the Bouguereau's hypothesis briefly in the last class, and we will basically elaborate it for all three dimensions in the present class, and then we go to basically deriving turbulence models. Okay, so this is the equations that we had derived last time for the compressible flows. Of course, when it is incompressible, your Rance equations this will go away, and your mass conservation also equation also becomes just del dot u bar equal to 0, right. But I am doing it for a general flow, general compressible flow, and incompressible is very easy if you can do it for the compressible flow, right. So, these are the terms that we had. So, we had this total stress instead of only the stress term, we had the total stress, which includes the laminar stress as well as the turbulent stress. The laminar stress we already have the formula, right, using the Newton's law, right, and this can be written as 2 mu Sij star, where I am using this Sij star to include this portion del u k by del x k, right, in the diagonal. And we have the turbulent flow, which is given by minus rho bar u double prime v double prime tilde, or in the case of incompressible flow, it will be like rho u prime v prime bar, right. In the compressible flow, we have additional heat equation. So, that gives us the thermal conductivity term will also have two terms, one due to laminar, that is the viscous diffusion, okay, and the other is the turbulent transport, right. So, this is the viscous diffusion of heat Qj laminar, and this is the turbulent transport of heat. Again, this is a term which needs to be modeled, right. So, there are two terms which needs to be modeled. I mean, at least actually this is a sixth term here. If you see, there are 6 stresses, and then you have a turbulent transport of heat term. So, how do we do that? So, we already discussed it in the last class that just the way the stress in a laminar flow basically is governed by the mean flow gradient. Same way we can think of that the turbulent stress or the Reynolds stress or the Favre stress basically is related to the mean flow gradient. So, that is a very bold approximation, but it works for most of the flows, and the idea behind it is basically if you look at any simple shear flow. So, if you look at even the stresses due to the eddies, they are somehow related to the flow gradient. So, if you can relate to the flow gradient, the problem of having 6 unknown stress quantities, basically 3 normal stresses and 3 independent shear stresses, can be reduced to one unknown problem, which is the eddy viscosity. So, what we said is for 1D flow, okay, if I can write it here, okay, let us say if this is your flow, I mean shear flow, okay. So, you can write it as tau turbulent, okay. I mean it will have two parts, the one will be the laminar part and other will be the turbulent part, right. So, laminar part of course is given as mu del u bar by del y, right, and we are saying that your turbulent part also gives the the stress as mu t del u bar by del y, okay. Now, it is very important to remember that mu t is not the property of the fluid. Here mu is the viscosity, which is the property of the fluid. Mu t is called the eddy viscosity or the turbulent viscosity, okay. This is not the property of the fluid, but rather it is the property of the flow, right. So, in fact, if the flow has very high Reynolds number, the mu t will be high. If the flow has low Reynolds number, means the velocity is small, or in general the Reynolds number is small, then this quantity will be low, and if the flow is laminar, this quantity will be 0. Now, this is good enough for like 1D flow. How do you do it for 3D flow, right? So, 3D flow, your stress term, so I can do it here. So, your stress term, as we have seen earlier, that this will be given by minus u prime, okay. Okay, let me write in incompressible only, okay, minus rho v prime minus rho w prime, these are the normal stresses, and then you will have minus rho u prime v prime, okay, minus rho u prime w prime, actually minus rho v prime w prime, right. These are the independent stresses, okay, and then we will have two terms here also. So, you can write it minus rho v prime u prime, which is nothing but minus rho u prime v prime, and here also you can have minus rho w prime u prime, which is because of symmetry it will be equivalent to u prime w prime, this quantity, okay, and this will be minus rho w prime v prime, which is equivalent to this, right. And if you use the definition that we had earlier using mu t, so what we can write, what is your strain tensor? So, that will be, this is 2 del u bar by del x, 2 del u bar by del y, and 2 del u bar by del z. Remember our earlier definitions, we had derived it this kind of expressions while doing the deriving the Navier-Stokes equations, and this will be nothing but del u bar by del x plus del v bar by del y, and similarly it will be del u bar by del x plus del w bar by, okay, no. Okay, so this will be du by dy, right. So, du by dy plus du by dx, not du by dx, okay, because these are the shear strains, okay. So, this will be del u bar by del y plus del u bar by del x, and this will be del u bar by del z plus del w bar by del x. Remember, turbulence is always 3 dimensional, okay, and there is what is the last term here, this will be del v bar by del z plus del w bar by del y, right. And what we are seeing that this is equal to this and multiply by mu t. So, again this term will be symmetric to this term, the term here will be, so this is x and w, so that will be symmetric to this term, and the term that will appear here will be symmetric to this term, right. Probably write it right. So, now if you add this, so if you use the business hypothesis, this all the stress terms should be basically found by just knowing this mu t, because we know all these quantities, all the gradients quantities are known by the momentum equation or mass conservation equation, and or basically the Navier-Stokes equations, right. Now, but there is one problem. So, if you add the trace here, right. So, what is the trace here? So, the trace here will be minus rho u prime bar plus v prime bar plus w prime bar, right, which is nothing but twice of the kinetic energy. So, basically minus 2 rho k bar, which is the turbulence kinetic energy, right. However, if you add these 3 terms, what will happen? You will this is written for the incompressible flow, right. So, it become 2 del u bar by del x plus del v bar by del y plus del w bar by del z, right. That is nothing but del dot u, and that will go to 0, right. So, there is a problem here, right. If you just use this definition, then it is essentially saying that my turbulence kinetic energy is 0, which is not possible. If the flow is turbulent, the flow has to have the kinetic energy, and it has to somehow accounted here in this formulation that we have, right. So, what we can do here is basically in order to make it physical, so that when I add the trace, it should give me the term which is minus 2 rho k bar. What we will do, we will just basically be adding the quantity which is basically minus 2 by 3 rho k only in the diagonal term, right. So, if you do that, equation will look like, let me put it here. Okay. So, your equation will look like, put mu t here, okay, and this will become 2 del u bar by del x minus 2 by 3 rho k bar. Okay, I am only writing the diagonal term, you know all the other terms, 2 del v bar by del y minus 2 by 3 rho k bar, and then minus 2 del w bar by del z minus 2 by 3 rho k bar, right. This is to make it consistent. We have other terms, CS test terms, which I have not written, and if you add these three, all these three, so this term will go to 0 because of the divergence condition, okay, and only what will remain is 3 into, so this will be 3 into minus 2 by 3 rho k bar, and this 3 will cancel out, and that will give you the minus 2 rho k bar, right. So, this is your final definition can be written in a short form, which is like this. So, this is your symmetric stress tensor. This is written mu t as Sij bar is basically nothing but, so Sij bar is del u bar del u I by del x j plus del u j by del x I and half of that, right. So, 2 of Sij is the entire tensor minus 2 by 3 rho k delta Ij, as we know the property of the Kronecker delta, that it will become positive only, or it will appear only when I is equal to j, right. So, that will only appear in the diagonal term, right. So, we got the value of the Reynolds stress here for the incompressible flow, and it is also consistent because if you take the trace of this, you are getting the correct value. Now, the same thing you can think for the compressible flow also. So, it is very similar to the incompressible flow. Now, the definition of the Reynolds stress is basically the Fowler stress here, and instead of Sij you will have Sij star, because this term should also come in the diagonal. So, basically it will be minus 2 by 3 del dot u. Okay, that will, when you add all this minus 2 by 3 del by u, so that will cancel out the divergence term which is appearing from the first equation, right. So, let me write it here. For the compressible flow, what will be the difference? There will be another term which is minus 2 by 3 del dot u minus 2 by 3 del dot u and minus 2 by 3 del dot u, right. So, derivative term, I mean, this is basically to make sure that when you add all these things, so if you add all the quantity on the trace, we just talk about the trace for the compressible, this is 2 del dot u, okay, minus 2 rho k, okay, and minus 2 del dot u again because of this term, right. So, although the divergence is not 0, this will go to 0, and this is, that does essentially give you minus rho k tilde, let me write it rho k tilde, because this is the power average turbulence kinetic energy, right. So, again this is consistent for compressible flow also. So, whether it is compressible or incompressible, we have reduced the closure problem to basically one single unknown, which is mu t, and for consistency we have used added minus 2 by 3 rho k in the diagonal term, right. As you see that this is heavily modeled, and we have used the physically consistent definitions, but again this is something which is not derived from the first principle, right. That is why it is called a model. So, that principle is called the Bouguereau's hypothesis, okay, as given here, or maybe the Bouguereau's model, okay, it was given around 1877, okay, or also called Bouguereau's eddy viscosity model, because we are not basically solving for stress, we are solving for the eddy viscosity model. Now, our known is nothing but this eddy viscosity, all other things are known, right. Now, as we saw earlier that we have another issue in the compressible flow, that we do not know this term, okay. There are many other terms which we neglected in the compressible flow, which were basically related to the viscous diffusion of the fluctuation term, or the correlation of fluctuation term, but this is the turbulent transport, okay. Basically this is the fluctuation which is uj double prime, which is basically transporting the heat, right. So, this is the term that needs to be found out. So, what we do is that it can also be written as, you can take the Cp inside and it becomes a rho uj double prime h bar, right. So, like we did for the velocity gradient, we will also relate it to the temperature gradient. Okay, same way like we do the molecular diffusion of heat. So, how do we do the molecular diffusion of heat? We have this k delta T by del x, right. So, this is power average. So, I am putting tilde here. Okay, so this is how you give the minus sign here. Okay, or k or lambda. Okay, let me use lambda here. Okay, where lambda is the thermal diffusibility or thermal conductivity. Okay. So, we will use a similar definition and we will say that our turbulent transport of heat is given by rho u j double prime h is given by a turbulent thermal conductivity which is acting on the temperature gradient, right, and that is how it is getting transported. So, this is by Reynolds analogy, okay, which relates the flow gradient or the velocity gradient to the temperature gradient, right. Now, our unknown is what is the turbulent thermal conductivity, right. So, if you recall, while non-dimensionalizing we had used the number called Prandtl number, okay, which was given by mu Cp by k, and we or lambda, write lambda here. So, lambda was mu Cp by Pr. Okay, so this was molecular diffusivity by the thermal diffusivity. We had used this definition. So, in the same spirit, we will define a turbulent Prandtl number. Okay, so which is given by Prt. Okay, and that will be mu T, viscosity Cp by lambda T. Okay, lambda T here. So, this is the eddy viscosity and this is the turbulent thermal conductivity. So, that way you can now define or write our turbulent thermal conductivity as mu T Cp by Prt, right. Now, Prt is the turbulent Prandtl number which is often taken as 0.9 if the flow is not very high speed and like it is not like going to like high hypersonic regions, then this definition works quite well, okay, especially in subsonic and low supersonic regimes you can easily use this definition. And now you can see that the only unknown we have still the mu T, right, all other things have been known. So, if you know the mu T, Cp is known for the gas and the turbulent Prandtl number is taken as 0.9 or around some that value, and you can get the lambda T. From lambda T you can calculate your rho uj double prime h bar, okay, and then you can close all the equations, right. So, all the unknowns that we had earlier in this, only these two were unknowns, okay, and then we had closed it by just using mu T, right. We use the Bouguereau's hypothesis as well as the Reynolds analogy. Okay. Now, all the models which basically relates the Reynolds stress or the power stress to the mean flow gradient come under the category of eddy viscosity model, right. So, we are looking for finding out mu T, right, which is the eddy viscosity, or you can write the kinematic eddy viscosity is nu T, which will be given by mu T by rho. Okay. Now, all the models eddy viscosity model, the one I think we might be using also k epsilon, k omega, SST omega. Okay, even there are some non-linear viscosity eddy viscosity model also. Okay, there are many variations of k epsilon, many variations of k omega. They are all based on this eddy viscosity model, and this works quite well for a wide variety of flow, and it is much cheaper than the Reynolds stress model, because Reynolds stress model, if you want to derive the dynamical equation, you need at least 6 dynamical equation, right. So, for each of the stress term, okay, and that will be very, very expensive. So, let us see how we can find out this mu T. So, again finding out eddy viscosity is not easy, and you cannot basically derive a equation from the first principle to find this quantity, but you can make some dimensional argument. Okay. For example, if you look at this nu T, this is has got the same dimension as nu, okay, which is nothing but meter square per second, right. Now, I am looking, so we have some scales in our mind, okay, from the eddy point of view. and we want to use these scales to basically find out the eddy viscosity, right. So, what are the scales that we have? So, for example, the length scale of the eddy, or maybe the velocity scale of the eddy. Okay. So, those kind of things that we know. If you see this, so in order to find this viscosity meter square per second, we need to have two things, one is the meter per second, another is in meter, and that will become dimensionally consistent. So, we need a velocity scale for the eddy, okay, because it has a unit of meter per second, and we also need a length scale for the eddy. Okay. So, you can write this nu t in terms of two scales, which is u0 and l0, right. So, what is l0? It is basically is the typical eddy size. Okay. Now, eddies can be of many different sizes, right. So, if you for example, if you see flow in a channel, so you have a very large eddy all covering all the way from the top to bottom, but you can have medium size eddies, okay, and then you can have very small eddies which are responsible for the dissipation. Recall our earlier basically picture of the eddy, and we had also talked about this picture of the energy content in the eddies. So, the large eddies take the eddy from the mean flow, and basically the lowest size eddy basically is responsible for the dissipation. So, this is for the dissipation, and here it takes the energy from the mean flow and call it production. Okay. In between they have a cascade of eddies, the largest eddy will transport to the next size and next size and next size and so on and so forth. So, it is not easy to find one typical eddy size. Okay. You have so many eddies present in your flow, right. So, which eddy size should you take? So, that is one problem. Second is, how do you find the turbulent velocity, right. So, one approach could be like take the u tau, as you if you recall in the boundary layer flow we have been using this scale which is very close to the. So, we had this tau w wall shear stress will be rho u tau square. So, you can define a scale of velocity which is tau w by rho, right, but then this scale is valid only near the wall. Okay. Your turbulent flow need not be confined only close to the wall, right. You can take the free stream velocity also, but that will also not give you the, I mean that is the mean flow. So, that cannot be used for the turbulent velocity scale, right. So, what is the best velocity scale you can think of? Again go to the dimensional argument. Let us say that somehow you know the turbulence kinetic energy K, okay, this is the turbulence kinetic energy, okay, which we have been writing as half u prime plus v prime plus w prime, right. So, if you know the turbulence kinetic energy, which is unit is meter square per second square. So, take the square root of that, the square root of k will become a velocity scale. So, in most of the turbulence model you use the velocity scale which is the square root of the turbulence kinetic energy. Again for that we need to find out what is the turbulence kinetic energy, right. So, the models like k epsilon, k omega, okay, or SST k omega or any variant of this basically try to solve a dynamical equation for the turbulence kinetic energy, and then you need another equation because we need to find out the length scale also. So, the other equation will give you the length scale, and that is how you find the eddy viscosity using these two scales, right. So, before going to those advanced models, let us look at what kind of models we have been we have seen in CFD, and this is from very early days of development of RANs, where we started with very empirical formulation, basically no equation for the turbulence kinetic energy or the length scale or anything, but use some empirical relation. Okay, so the first is like people have tried with constant eddy viscosity. So, just by the information that eddies contain energy and the viscosity is basically higher, I mean the mixing is much higher than the normal viscosity, laminar viscosity. So, you can take the viscosity as like let us say 10 times of the laminar viscosity or 50 times the laminar viscosity and see how the performance is. Second is you can use this L0 geometrically, that means that let us say that if you have a channel flow, right. So, your eddy is confined, it cannot be bigger than this, right. So, you can use some fraction of that length based on the geometry, you can use that as your length scale. and then you can use this u0 from the mean flow gradient. So, you know the mean flow gradient, somehow you can use the mean flow gradient to get this u0. So, basically you are not solving any additional equation, only the 4 range equations that you have, you are going to solve them, and so and you get the value of u0 and l0, and you that way you calculate the nu t, right. So, this is called the zero equation model. Then there are half equation models. That means that instead of solving a PDE, so typically the models, the equations that we get, we will be seeing the continuity equation, mass conservation equation, momentum conservation, they all solve PDE, right. So, instead of solving a PDE, we can solve an ODE, right. So, it is easy to solve. So, these kind of equations are called the half equation model. So, one example is the Johnson-King model. Then we have one equation model. So, typically in these kind of models, we specify the length scale geometrically. So, L0 is basically given by the geometry, by the size. If this is a free shear flow, maybe the wake width or the jet width, all those kind of widths you can take, boundary layer thickness, those kind of things you can take for your length scale. And then but you need an equation for the u naught. Okay. So, these kind of models are called the one equation model. Okay. And then we have two equation models. So, we have to basically get the equations for both the length scale as well as velocity scale. So, we are not using any geometrical parameter, and the problem with the geometrical parameter is that if the flow is complex, right. So, then this length scale is changing everywhere, right. Let us say you have a configuration which is going like this, okay, something like this. Your basically your width is changing everywhere, the flow is changing everywhere. So, if you use a geometric scale, let us say you define it based on this length, okay, this may not work here, this may not work here, and so on and so forth, right. So, geometrical characterization of the length scale is not suitable for complex flows, right. So, let us look at some of these models. So, this is a big picture of the turbulence models. So, we are now into the eddy viscosity model, but as we told that we can the another approach is the Reynolds stress model. This is more expensive because we use 6 models for 6 different stresses. Okay. In the eddy viscosity model, the only thing that we need to find out is mu t, but then it depends on some length scale and the velocity scale that you need to find out. Okay. So, first is basically the linear model. So, broadly speaking, let us say that your stress is linearly dependent on your velocity gradient. Okay. So, then it is a linear model, and if it is non-linearly dependent, that means that you have additional terms here instead of just not only mu t, but let us say mu t square or some other things. Okay, then it becomes a non-linear model. So, this is to basically make the model more and more complex, so that it can address more complex flow problems. So, we have the zero equation model. Okay. For example, the Prandtl mixing length model, we will discuss that in the next class. Okay. Then we have the Baldwin-Lomax model, which is also the zero equation model. There are many more models, I am not going to discuss here. There is a Cibicki-Smith model. Okay. Then there is a one equation model, like Spelett-Alamedas model is a one equation model, very popular model for external dynamics flow. Let us say you want to simulate the flow over a wing, you can use the Spelett-Alamedas model, but this model does not use a length scale, okay, only the velocity scale. So, this may not be suitable for flows which are very sensitive to the length scale, for example, flow in turbine blades, like in the turbo machinery flows. Then we have the two equation models. So, broadly the most popular models are k epsilon and k omega. Okay. And then there are further categories to that. We have the standard k epsilon, realizable k epsilon, RNG k epsilon. So, once the k epsilon model has been derived, there have been very many variations of the k epsilon over time. Okay. And people basically try to fit the coefficients or the definitions of the transport equation, especially for the turbulent dissipation rate, which is epsilon here. Okay. So, you can see here k and epsilon, but ultimately what you are trying to find out is the L naught and U naught. Okay. We will use this parameter of kinetic energy and the dissipation rate to get this U naught and L naught. So, U naught is fine, you can just take k to the power half. Okay. And using the dimensional analysis, we can also find the L naught from epsilon and k. Okay. So, there are different models which have been derived over time. Okay. Then Q omega model. So, is a famous ones are basically Wilcox k omega, and then Mentor's SST k omega. Okay. And then Wilcox also has many variations. Okay. So, if you go to the NASA turbulence site, Okay, you can see different models and how they have, when they have been proposed. So, if you are going to use these models in your for your simulation, make sure that you know that which model you are exactly using and what are the parameters that you are using. Okay. Then we have nonlinear models. Okay. So, this is of course will be more expensive, okay, but this is suitable for some kind of non-equilibrium flows. Okay. So, for example, cubic epsilon is one model, EARSM, okay, which is another model. Okay. Then you have V2 omega model, which is a relatively new model, but this is becoming very popular recently. So, these are the models. Apart from these, you also have the transitional models, okay, which have not included in this. Okay. So, the point here is that these models are good for fully turbulent flows, okay, but there are regions, for example, if you look at the typical boundary layer profile, okay, the flow is laminar here and then turbulent here. Okay. This is laminar and this is turbulent. Okay. So, in between the flow is transitional. Okay. So, how do you find out the transition region and how to model this part? Okay. So, that is also a matter of research. Okay. This is very common in most of the flows, right. So, where there will be some region which is transitional. The transition can be natural transition, the bypass transition, it can be separation induced transition. If you have a separation in your flow, that can also become transitional, right. So, then there are models which basically account for the transition regime also. So, there are two model which are most popular. One is the is basically 4 equation k omega SST model. Okay. In this, apart from this 2 equation of k omega SST, you have 2 more equations for, one is for intermittency gamma, another is the momentum thickness based Reynolds number R e theta. The second is the laminar kinetic energy equation, okay, laminar kinetic energy equation or laminar kinetic energy model, LK model, okay, which has not only the turbulent kinetic energy KT, but also KL. Okay, you also solve for the laminar kinetic energy, okay, because as I have been saying that in the transition regime, the flow is neither laminar nor turbulent, it is in between. Okay, flow is trying to become turbulent, but if you give the sufficient favorable pressure gradient, it may become, it may go back to laminar also, right. So, we will start with some very simple models like 0 equation model, and then we go to the 2 equation model, and then we will look at the k epsilon k omega SST k omega, and that is how we will finish this discussion about the turbulence modeling. So, we will see you in the next class. Thank you very much.